In this tutorial, we are going to do another tutorial on MSC Nastran Solution 400 results. And the example we're going to be looking at today is an example in chapter 33. So here we have this lap joint, and we're essentially going to fix the lap joint on one end and we're going to pull on the other end. And if you look here in the middle, we have three fasteners that are going to be modeled with CBUSH elements. And in this tutorial, this is what we're going to do. We're going to create some of the result plots that you see in this document. So if I scroll down a little bit more, you're going to find a plot for the equivalent stress in the 2D elements. So we're going to create this plot. Then you have a deformation plot. We're also going to go ahead and create this. And then we're going to look at some of the shear forces on the fasteners that are being modeled with CBUSH elements. So here you can see the shear forces are range between 748 and 825 newtons. And I should mention that this example that we're looking at right now, this is in the document, the MSC Nastran Demonstration Problems Manual, Implicit Nonlinear. And again, we are looking at chapter 33. So if we go back here, we're going to be using the post-processor web app to look at some of the data that I showed a moment ago. We're going to be looking at the displacements, equivalent stress, and the shear forces in the CBUSH elements. So let's go ahead and close this. Let's go to the home page of the SOL 200 web app. So today we're going to be using one tool called the post-processor web app. So before we go ahead and get started, let me go ahead and point out a few bullet points. Number one, the post-processor web app is free for MSC Nastran users. If you're a student, researcher, or professional engineer, the post-processor web app, again, is free for you to use. Also, the post-processor web app is only compatible with MSC Nastran. This web app is not compatible with any other version of Nastran. So now that we got that out of the way, if you want to start using the post-processor web app today, you can visit theengineeringlab.com. Here at the top right, there's a button called free download. Click that button, fill out the form, and we'll let you download an installer for the post-processor web app. Alternatively, you can get online access where all you need is a URL link to go ahead and start using the post-processor web app. Now, to start off with, let's go ahead and make sure our downloads directory is empty. You're going to be downloading a few bulk data files, and it's better to avoid any confusion with other files. So here, once you're in the home page, click on Tutorials and User's Guide here at the bottom center. And when you open the User's Guide, you're taken to the Post-Processor Tutorial section. Scroll down until you find this example. CBUSH CFAST CWELD, Shear Forces and Fasteners of a Lap Joint. So let's go ahead and click this link. And now if we look at the downloads directory, we have the zip file that contains the bulk data file and the H5 file. The bulk data file contains the finite element model. So let's go ahead and import that bulk data file right now. And the H5 file contains the results of this Solution 400 analysis. So what we're going to do next, we're going to go to File Upload H5 and select that H5 file, and we're going to upload it to the web app. And once you do this, the post-processor web app is going to open automatically. You can see that the first plot that's created is a deformation plot. So here, let me go ahead and change the background color. And so here you can see what the deflection or deformation looks like for the lap joint. You can flip through the different subcases. So let's go ahead and do this. And here we'll just take a look at the final subcase and final time step. And maybe let's go ahead and maybe make this a scale factor of 1. So let's go ahead and go back here. And then I think there is some rotation in this model. Let's go ahead and find out what the load is. Okay, so here what we're doing is we're applying a tensile load of 2400 newtons to the right end of the upper plate, which is normal to this edge and parallel to the plate. Prior to this loading, make a rigid body rotation of 45 degrees about the global y-axis. So let's go ahead and do this. Let's not worry about the time steps that rotated this by 45 degrees. Let's just go ahead and look at the time step where we pulled on it. So that would be this time step. Let's go ahead and exaggerate the deformation. So we'll go ahead and use a scale factor of 10. And so that's the first plot, a deformation plot when we pull on this lap joint. Now let's go ahead and look at the equivalent stress in the 2D elements. So here for select data set, let's go ahead and select stress quad NL for nonlinear, and we'll go ahead and select that same step. So here we selected step 1 for time 1 and subcase 1. And if we scroll down a little, let's go ahead and select this field or quantity or response, equivalent stress at Z1, the bottom. So here we get an element by element plot of what the equivalent stresses are for the bottom thickness. And here, if you want to know the direction of the bottom thickness, this is what you can do. Turn off the display shape plot button. So now it's white, so it's turned off. For display directions, set that to yes. When you do that, you get a plot of the element coordinate system, and here in blue is the positive Z element axis. So here you can see that this is positive Z. So the top thickness is somewhere up here, and then the bottom will be somewhere underneath. If you really wanted to, you could use the model display panel to turn on the thickness. So here I'm zoomed out. So again, we saw a moment ago that with the aid of the element coordinate systems, we know that this is the top of the thickness, and then this is the bottom of the thickness. So if we go back into post-processor mode, here on the right, you can see that we're looking at the equivalent stress for the bottom of the 2D elements. So you can imagine there's a thickness here, and we're looking at the bottom equivalent stress. If we wanted to know what the equivalent stress was at the top of the thickness, we can go ahead and select field ES2, equivalent stress at Z2, or the top. And now we're looking at the values at the top of the thickness. So that's how you look at the equivalent stress. And now let's go ahead and tackle the hardest part in this whole exercise, the shear forces in the CBUSH elements. So scroll down here. There's a table provided in the document that gives you an idea of what the shear forces are in the CBUSH elements. So here, this is what we're aiming to look at. We want values of shear forces that are on the range of 750 and 825 newtons. So let's go ahead and take a step back, and let's go ahead and find where the CBUSH elements are. And what I went ahead and did, here in the model display panel, I've turned off and on the CBUSH elements. So if you zoom in very closely, let's go ahead and turn them off and then on and off. If I go to the Fem label tool, I can click on the CBUSH element, and then I can turn on the display grids. And then here I'm being told that CBUSH 338, it's connecting grids 277 and 144. So now that we have the CBUSH elements displayed, now we can look at the element forces. So let's go ahead and select the element force BUSH dataset. And let's go ahead and select the first checkbox. And once that data has been acquired, here we can select different forces and turn on the arrow plot here. There's a button called arrow plot. Let's go ahead and click that. And if we zoom out, we actually get some arrows regarding the forces that are acting in the CBUSH elements. But we don't want to look at the forces along the x-axis. So let's go ahead and turn that off. And then we just want to look at the shear forces along the length of the lap joint. So if we look closely, and sometimes it's a little hard to look at this, so what we can do is we can jump into first person mode, And let's go ahead and use first person mode to really look at the CBUSH elements up closely. So let's move sideways a little. Let's go ahead and move sideways. And now we're in between both thicknesses or 2D elements. Let's go ahead and move around a little. And what we're after is this value, Fy. That's the shear force we want. So let's go ahead and turn off Fz. And now I'm only left with the shear forces along the length of the lap joint. So let's go ahead and look at this other value. So if we look at this first CBUSH, we're getting a shear force of 825 newtons. And if we jump back to the document, you can see that for the first CBUSH element, we are getting 825 newtons. And let's go ahead and repeat the process for the next CBUSH. So let's go ahead and maybe move forward a little. And here you can see that the arrow is telling us the direction of the shear force. And then this shear force is about 748. And if we go back to the document, we get 748. And now let's look at the last CBUSH. So what we're going to do is move forward a little. We're walking, we're flying. And then here we have a shear force of 825. And that will be the third column in the table. So that's how you look at shear forces, or rather the element forces in the CBUSH elements. Let's go ahead and exit this mode. Let's go back to the original way of looking at the model. And let's zoom in. Say you prefer to use this method to look at your shear forces. How can you hide some of these items? Let's go ahead and open the model display panel. Let's go ahead and turn off the coloring for the element faces. And now let's go back to the post-processor web app. And if you zoom in, this is your CBUSH that's connecting the two nodes. And here you can see that we have the shear force for this element. Now, comment about whether the spring is in tension or compression. We actually use two arrows to help you understand if this is in tension or compression. If the two arrows are pointing away from each other, then you have tension. If the two arrows are pointing towards each other, then the spring is in compression. And let me hide the force along the Y value, and let's zoom in a little bit closely. This coordinate system that you see here, this is the CBUSH element coordinate system. So this is very important when you're looking at results because all the element forces are being observed in the element coordinate system. So this is something that you can look at here in the post-processor web app. And now one last thing for this exercise. Say you wanted to write out all the CBUSH element forces to a CSV file. What you can do is open up the HDF5 Explorer. And once you open the H5 file, let's go ahead and select the element force BUSH dataset. And here for specify entities, if you know which element IDs you want, you can type in the IDs here. If you want all the elements, you can type in all and click acquire dataset. Here you can see that I have all the element forces for all the time steps or subcases and steps. I can download or I can click on download CSV here on the top right. And now I have a table with all the element forces for the CBUSH elements. Now I can go ahead and do some hand calculations if I wanted to. Now, if you wanted specific results from a specific subcase or step, there's a checkbox here called select domains. You can click on that. Let's go ahead and move this to the right a little. If you wanted to select results from a different domain, so from a different step or subcase, you can mark the specific checkbox here, click acquire dataset, and this will go ahead and acquire the results just for that data or that domain. So here you can see that we've acquired data for just those specific domains. Okay then, anything else here to look at? No, I think we're pretty much done with this exercise. Just one last comment. This example involved the version that has CBUSH elements. There's also a version with CFAST and CWELD elements. And let me scroll down here. If we look at the input file we used today, we use model A. So here, nug underscore 50A. That's the version we use today, the version with the CBUSH elements. If you want to, you can follow along with the other versions of this model. So there's a B and a C version. B is using CFAST elements and C is using CWELD elements. So both of these, or all three of these examples, will work with the post-processor web app. And now let's go ahead and go back to the homepage of the engineering lab. So again, all the tools that I showed you today, the post-processor web app and the HDF5 Explorer, both of those are free as long as you are an MSC Nastran user. Also, if you go to theengineeringlab.com, at the top right, there's a free download button. Click the buttons, fill out the form, and then we'll start working on getting you an installer for the post-processor web app. So with that, I'll stop here. And as always, thank you so much for watching.